sorry. Okay, let me say this again for the recording. For the exam on 24th, the crib sheet that is letter size, front and back is allowed. Scratch papers allowed. Calculators, basic scientific calculators are allowed. Okay, these are things are allowed. Okay, and also ACI code is allowed. Okay, ACI code 318 code is allowed. Okay, for things are not allowed, the textbook is not allowed. The notes are not allowed. Okay, all right, so these are materials for the exam. Now for the length, the problem, the exam number 1 will take about 2 hours. Right now, I'm debating between 3 and 4 problems. I'm inclining to have 4, but depending on the preparation, I may cut down to 3. I think 3 is just easier for you guys to do, but again, each problem will have more percentage weight. Okay, so that's the subtle difference. And I try to control the exam to be within less than, say, half an hour for me to solve it. And for you guys, 2 hours, I think that's sufficient. Okay, all right, so that's about the exam. About the study, you will try to study homework first, homework number 3. And for homework number 2, I have given that to the TA. He will upload the grades together with homework number 3. And we will do that before the spring recess, which is this week. All right. So homeworks number 1, 2, 3 are the ones you need to review. And lecture notes from the beginning, from chapter 0, that's 3 PowerPoint printed out versions for you guys to study the basic concept of things, to last lecture, irregular section, to last lecture, irregular section. Those are everything you need to study, okay? So from today on, all the materials will be covered today on will be counted towards second exam, okay? Will be counted towards second exam, all right? Okay, so that's some materials you need to study. And also, I have posted one formal exam in the files folder on Canvas. Please take a look at it, work it out. Please work it out. I'm begging you, please work it out, okay? Now, we will have office hour tomorrow. Please note it down, 1 to 2 p.m. And again, I'll email everybody using the same Zoom link. We have office hour tomorrow, 1 to 2 p.m. afternoon, Tuesday, using the Zoom link. And again, it will be recorded. It will be recorded. Everything we do when we do online will be recorded, okay? Will be recorded. And in the review hours, I will go through the previous exam I posted, and I will answer the questions, okay? And I will not tell you what to be tested, but I can give you a general framework or envelope of what should be covered. All right, so that's everything I have right now to say about exam. And just in case I forgot, if you need reserve a testing room, please do so right now. Don't wait till last minute, okay? They seem to get very crowded before the day of testing. So please request right now, okay? So I can approve it, all right? Okay, other than that, do we have any questions about exam number 1? Are we ready?
Are you, so you have the TA proctoring that test then, since you're going to be back on April 1st?
Yeah, no, I mean, that's different, right? So Drew, we need to talk to I need to talk to you a little bit afterwards, but I will be back in April. So everything will be back online in April. That is after spring break. The grader is already back. He is doing the grading, but he is handling number 3. And
but we still have to show up on the 24th in class to take the test.
Oh, you mean the proctor, right?
Yeah.
Yeah, the proctor, I have 2 students be there for the exam. One is a TA, and the other student will be a PhD student from my group. So we have 2 people, 4 sets of eyes, and to ensure everything goes well, okay?
All right, very good.
Yeah, no problem. And also for the homework, for the grading, if you have any dispute about the grade, don't go to TA, come to me, all right? If you have any grievance after seeing the grades, and the TA is working hard at home number 3 right now, and he promised me he'll try to get everything done before 17th, okay? And then after he upload the grades by the spring recess, take a look at your grade. If you have any grievance, let me know. Any grievances, let me know, okay? Send me email, don't bother him, okay? Send me email, I will be able to rectify it if anything that is inconsistent, okay? And that's about the grading. And the last but not least is that if you need more materials to study for your exam, come talk to me tomorrow, Tuesday, okay, 1 to 2 p.m. I need to see where you're at and I need to see what kind of problem you have so I can determine what kind of additional materials you might need for the exam. All right, okay. Anything else, folks? Anything else? Anybody? Questions about exam number 1? Very important exam, okay? Very important exam. Anything else? Okay, so I know some of you have time conflict tomorrow, but please try to show up tomorrow 1 to 2 p.m. If not, watch the recorded video for tomorrow. I'll list this office hour upload to YouTube as well tomorrow, promptly after it's over. So please watch and go over them, and we can talk about it this Wednesday, okay? We can talk about it this Wednesday as well. All right, okay, without further ado, let's continue. Let's continue. So today, we're going to start a new chapter, that is shear design. Shear design. So lecture 11, shear. Okay, shear design. Okay, all right, so we have talked about bending. Right? So if I take one element, and this is kind of review from the fraction mechanics, mechanics materials, okay? And you know that if I do a small element, this is 2D, okay? And I have compression, and I have tension perhaps, and these are called normal stresses, right? These are called normal stresses. And these are the stresses we're talking about induced by flexure or bending. Induced by bending. Okay, and flexure. Okay, and also you may have another type of stress that is stress on the surface. Stress on the surface, right? And that, ladies and gentlemen, is called shear stress. Shear stress. And these are typically induced by shear force. Shear force. All right. So these are two types of stresses exerted in the beam by the external loading, right? So right now, so far, we have mainly talked about the flexure stress, right? So exam number 1 basically covered the normal stress design. All right, that's where we were at exam number 1. And now we should start looking at the shear stress. Shear stress. Okay, so to give you a general concept of what type of shear stress we're dealing with, let's pull out our old friend, right? Pull out our old friend of the simply supported beam case again, right? So for this case, I'm drawing a little bit deep. I'm drawing the beam a little bit deep so to show the shear stress. And let's just say it's a simply supported beam, right? So left side, I have this nicely built hinge support. Right side, I have this, left side, the fixed support. Right side, I have this hinge support, okay? So meaning on the right-hand side, I have 2 restraints, vertical restraint, horizontal restraint. And, on the right-hand side, I only have 1 restraint, okay, vertical restraint. On the left-hand side, I have 2 restraints, vertical restraint and horizontal restraints. Okay, see, these are the reactions of the flexure of the beam, right, of the beam. Now, for this beam, and you know it, and we usually have an external loading exerted on top, and let's just say that is in terms of distributed loading, okay? In terms of distributed loading. All right, in terms of distributed loading, right? This is what it looks like. All right, so under the distributed loading, right? If I say, let's just find the middle section, right? Cut the middle section and say this is section AA. And I want to investigate the stress along this section. I want to investigate the stress along this section. Okay, what kind of stress I will have. Okay, Natalie, we were able to pull out the Zoom class. Everyone's on their own device mostly now. Okay, Natalie, that's fine. Let me ask you, Natalie, can I get a head count from students who does not have Zoom or own devices in the classroom? I just want to make sure everybody has access.
We've got about 2 people per laptop in the classroom. So we've got like 5 laptops and then 2 or 3 person per laptop.
Okay, so I feel so sorry about it. And now everything will be recorded. If you miss anything, I'll shout out loud, but if you miss anything, please go back and review the recorded lecture, okay? And if you have any question, come to me, okay? All right, so come back to this stress state in the middle section, right? So looking at this view right now, I say that the middle section looks like AA right here, okay? And I say that the neutral axis right here along the line like this. So this is my neutral axis. This is my neutral axis, right? And before you know it, right, we talked about this before in the last lectures, or actually several lectures before, right? I said, if this is AA, I'm putting the strain diagram or stress distribution, right? So stress diagram, this is stress. And now I want to emphasize, this is normal stress, okay? Normal stress. Or if you want to say that, that's the flexure stress, flexure induced stress. And this is in the section AA, section AA, okay? So it follows the strain diagram, and this assume everything's elastic, okay? Assume elastic, assume elastic. Now, what does elastic mean? Means that the concrete is not here, right? Assume some magical material can handle tension, okay? This is not the concrete, it's just some materials, okay? Elastic materials, okay? So the stress will look like this. Actually, on the top, we have compression, right? And on the bottom, we have tension. All right, so on the top, we say this is compression, and at the bottom, we say this is tension. This is tension. Okay, and if I want to say it precisely, I want to quantify, right? Define, quantify, and judge, right? That's the logical sequence right here. So how do I calculate the stress? How do I calculate the stress, right? So you say that if this is stress distribution sigma in terms of the height h, or let's just call it y, and y is in terms of coordinate system of vertical coordinate system, right? So this is y. Okay, so sigma as a function of y should follow the old stress equation, right, from mechanics materials. But new moment must by y over moment of inertia I, moment of inertia I. So that is the normal stress. All right, that is the normal stress. Okay, so if this is the case, let me start trying to investigate, right? I say, look, if this is a normal stress distribution at the middle section of a simply supported beam, now if I have several elements, along this section, let's just call it element 1, element 2, element 3. And I strategically place these elements in 1 on the top of the section, 2 right in the middle of the section, 3 at the lower bottom of the section, right? So I want to see that what type of stress I have in terms of normal stress, okay? In terms of normal stress. Now I look at here, I say, look, fine, element 1 here, element 1. So I'm just start putting element 1. It should look like a nice nice square element, and this is 1. And I know that this is right here on top of here, right? So here is a compressive stress, right? So compressive stress look like this. Now, you know, this is element, right? This is the element. So I have compression on the top. I have compression on the top. So the balance out of equilibrium dictates that I need to have another compressive stress coming from the left side, So this is the compressive stress for element number 1, okay? Element number 1 in the normal direction, okay? So let me just write it down. I say, look, this is normal stress, sigma, and I call it 1. I call it 1 because this is element 1, all right? And so that is the normal stress. All right, so after talking about the normal stress, right? Let's take a look at the shear stress. So I still do the same cross section, right? AA, cross section AA, okay? And I seem to recall that the shear distribution is quite different from the normal stress distribution. How different? The shear stress distribution follow a parabolic line like this. All right, follow a parabolic line like this. Okay, and start from 0, goes to the maximum value right here, and then go back to a 0 value. Okay, so that is my shear stress. And you notice that in terms of normal stress, I have these tiny arrows, right? Indicating the direction, right? But for shear, some reason I did not have arrows, and I'll explain to you why, okay? So I only have these lines indicating magnitude, but I don't have arrows indicating the directions, all right? So something just keep in mind. And I know that here in the exactly the location, the neutral axis location, right? I have the maximum shear stress, and let's just call it tau max. All right. And actually, if you recall from the stress distribution, right? Stress distribution, shear stress distribution is tau is equal to V. That is the total shear force exerted on the section A, and Q, which is the static moment, okay? And divided by IB, divided by I, which is the moment inertia, B is the width of it. And if you say, Bob, I already forgot about it, right? So let's say this is rectangular section, this is rectangular section, and I am trying to find the shear stress located here, right? And this is the neutral axis, right? This is neutral axis. And let's just say that this is Y, okay? And this is half H, half of the height, and this is half H, half of the height, right? So these are the geometries, right? So if I were to find shear stress, right? So what is my V? V is the total shear force, right? So if you look at this distributed load, let's call it omega distributed load, and let's call the span length to be L. Now I need to pick up a victim here, Alex Durbin. Alex.
Yeah,
How are you doing? Doing all right?
I'm doing great.
Good to hear that. So quick question for you. And if I have distributed omega, and let's just call it omega u, so that means the factor, right? Including the 1.2 and plus 1.6, right? And I have a span length of L. What is my total force exerted on the beam here? P. Equivalently, PU equal to?
It'd be the distributed load times the length.
Exactly, right? So if that's the case, what would be my reaction force?
It'll be your P divided by 2.
P divided by 2, exactly, right? So that is my P divided by 2. And now, so here is my reaction force on the right and left, and this is my reaction force on the right, and that is also PU over 2. So if this is the case, what will be my shear force at section AA? Shear force. Give you a hint. Think about the shear diagram. Remember the shear diagram, Alex? See there?
Oh, yeah.
So that's okay. Quick flash loss of memory, right? So let's take a look at the shear diagram. Thank you, Alex. Being very helpful. And so if you think of a shear diagram, and let's just overlay on top of it, right? So at the left, right, I have this force here. So if I do shear, has to balance this force, so it's be constant, right? But now, as I have these distributed loads, I'm going down, right, to a certain value here, and what is that value? 0, right?
Yeah, I remember now. 0.
0, right? It is 0, right? So if that's the 0 here, I flip back here, and then to the PU value here, right? PU value here, right? So unfortunately, thank you, Alex, again. Unfortunately, in this case, I picked the wrong case, right? So because VAA here is actually 0. In the middle section is 0, isn't it? In the middle section is 0. Okay, so here I shot myself in the foot, right? I shot myself in the foot, okay? So in this case, actually, I have no shear stress at all in the middle section. So that means in this case, I have 0 shear stress, and everything back to a flexure being designed. All right, but if I want to take a look at the shear stress alone, right? What I need to see is that I have a maximum shear stress at the end of it, right? And that's half maximum shear stress at the end of it, right? So that's where the shear stress should be looked at. So in the simply distributed loading, what I end up have is so-called stress decoupling. That means the maximum normal stress happens at the different locations of the maximum shear stress. All right, maximum normal stress happens differently, okay, from the maximum shear stress. So for a simply supported beam, you don't really worry about shear, right? For the middle section, you don't really worry about shear too much, right? You worry about the bending moment. That is the normal stress design we have talked about. Okay. All right, so this is what the stress regime look like, right? But I want to continue with my lecture, right? And remember, I just did element 1, 2, 3. It would be such a waste not to continue that, right? So let me play a magic. I say, look, mistake made. let me make a correction. I said remove this distributed load, remove this distributed load. Instead, I'm going to have a concentrated load PU only, right? Concentrated load PU only, okay? If that's the case, my shear diagram changes, right? My shear diagram changes. Start from a certain half PU still at the left end and go straight and sunk to another half PU, then go straight again, right? So this is half PU again, okay? This is half PU again. So if I have concentrated load, right? So my shear force is the same here, 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 here throughout. And in the middle, I have half PU here, half PU here, and the right-hand side of half PU there. All right. So now if I say I have concentrated force, I'm looking at the middle section here, right? My shear distribution will look like this as I just draw out, right? As I just draw out, it will look like this now because I now have shear stress. And now the shear force in the middle section right here, shear force in the middle section right here is no longer zero, ladies and gentlemen, no longer zero. That is PU over 2. Right? So that is shear force at middle section A, right? Now, look at, we have V check, right? So that is V, fine. And let's look at the bottom first, right? B is the width of the section since I have rectangular. So naturally, this is my B. And that is checked, right? We know that dimension, right? So what about I? I is the moment of inertia for rectangular beam. Austin, Eisterhold.
Yep.
Hey, how are you doing, sir?
Good. How are you?
Not too bad, not too bad. So can you help me out here? For moment inertia I for rectangular beam, what is the equation for it?
112 BH cubed, right?
Perfect. Thank you so much, Austin, Big Saber, right? So that is the moment of inertia. So we know it. We know it. The only thing, and this kills most of the class when I taught mechanics material, right? That is the Q, right? What is Q? And now Q is so-called static moment. Okay, static moment, that is the area of the shaded zone, which is the area of the shaded zone that is away from the location, and multiply the distance from the centroid of that zone to the neutral axis, right? So if I call it D, and this is A, so Q would equal to A area multiply D. Okay, that is called static moment. So now if I can do this, I can find out the stress at this location, right? At this location, maybe correspondingly somewhere here, right? That's corresponding somewhere here. All right. Okay. Well, but you are in luck. Why are you in luck? Because you're in reinforced concrete design class. This is a design class. So sorry, no more complication about this mathematics and the mechanics materials. Goodbye, mathematics, right? Welcome empirical equations, right? So don't have to remember all this, but it would be very good if you still remember where they come from, right? But for our purpose, intended purpose, we just need to know that for one, I have some shear stress, right? And matter of fact, if I take a look at the shear diagram, right? Take a look at the shear diagram, right? So let me just do a free body diagram on the left-hand side of it. This is my reaction force, half PU, fine. And I'm trying to balance that. If I do a cut, right? Remember, if I do a cut like this in the middle, right? On this side, exposed surface, I need to balance this. So this arrow should go downwards. So naturally, that is my shear stress, and that has to go to downward direction. Okay, downward direction. All right. Now, if this is downward direction for element, remember I am picking the element 1, and preserving, or we call it rotation conservation, right? Rotation conservation, okay? And there's another one more complicated than this, Latin word, but let's don't go there. For rotation conservation, right? Meaning that I have to balance the block so it won't spin, right? And now I require all my shear stresses has to have the sign, the error against the error, tail against the tail, error against the error, tails against the tail, and everywhere is tau 1. Same magnitude everywhere, so that I will not resulting in a spinning moment with respect to the centroid of this element, right? So that, ladies and gentlemen, is all the stresses I have. All the stresses I have on element one. On element one. Okay. All right. So this is all the stress I have on element one, right? On element one. So I say, look, it's a nice stress, right? Yeah, it's a nice stress. And I say, I want to see if this is all the stress on element one, what it should look like, right? So that is the compression, and I have shear stresses. Compression, I have shear stresses. So I want to see how it fails. I want to see how it fails, right? So how it fails, Anyone? Anyone can help me? So what do we need to do? Well, again, a little bit of mechanics materials, right? We need the principal stresses. Okay, principal stresses. So what do you mean by principal stresses? It means that I want to find out the combined stress state. Okay, so in this case, I can always rotate the element. Okay, and be careful when I say that. I can always rotate the element and turn the thing into a pure normal stress state. Okay, that means only compression and tension. Okay, I can do that, right? So it turns out if I do that, right? I can convert this thing back into a normal stresses. In this case, since element one, I don't have a whole lot of shear, right? So as I'm moving away from this location to across close to the top of it, my shear stress diminishes, right? So primarily, I only have compressive stress, right? So that is, sorry to do it again, but that is, I most likely will have a slight rotation, but mainly the stress will be the compressive stress dominance. All right, mainly the compressive stress dominance. And then the failure will look like something like a 45-degree line somewhere, right? 45-degree line somewhere, right? But that is something we will show later, okay? But this is all the stresses you have seen in element one. Okay, so now that is element one. How about element two? Element two. I say, Bob, element two is just a numerical addition. 1 + 1 = 2. That's the second element, right? What's so special about it? Well, what's so special about it is where element two is at geometrically is right here at the center of the simply supported beam, right? Center of the simply supported, kind of like us, right? Right in the center of America, right? Right in the center of America. So with element two in the center, what benefits do I bring? So I want to remind you that element two is in the center. So that means it's at the neutral axis. It is at the neutral axis. And I'm trying to find a guy to blame again. Danny Wilson. Hello. Hi, how are you doing? Doing all right?
Yeah, I'm doing good.
Good. Glad to hear that. And can you help me out, Danny? So if my element two is sitting on the neutral axis, right? Let me give you a tip. Sitting on the neutral axis, what will be the stress for element two in terms of normal stress?
Tension, compression.
Well, think of it, right? So it's on the neutral axis, right? This is a stress diagram, right? Right? So it's sitting right here. And then what will be the stress for element two?
Would it balance each other out? Maybe?
So it will be
0.
There you go. Nice. Thank you so much. Then 0, right? So that means I benefit from it because I know exactly there's no normal stress in element number 2, right? So just like Danny says, they cancel it out, right? It's right in the middle, so there will be no normal stresses. However, don't forget, right? We are sitting in the neutral axis, right? So following the diagram, the shear stress though is at the maximum. So when I draw my stress diagram, I know I don't have any normal stresses, but I do have shear stress, right? And just to put it there, so this is tau 2 maximum, tau 2 maximum. All right, so that is my shear stresses. Again, I want to study the principal stress, right? I want to figure out if I rotate the plane and to see if I can have a pure normal stress state, right? Pure normal stress state. And this thing, if I do that, and now I can spin it in a 45-degree angle, right? 45-degree angle, because now I have a pure shear stress. I have a pure shear stress. So it looks like that I will have a 45-degree angle, and this will be my pure tensile stress generated, and my failure line will look like this. Okay, my failure line will look like this. So long story short, if I do this again for my element 3, I will see the same block again, right? The only difference is now if this is 2, my element number 3, I have now tension stress, right? Since it's at the bottom, so tensile stress, right? And now that would have tensile stress, sigma 3, and then again shear stress, right? And this is tau 3, and again tau 3. So that is my stress state. All right. Now, if I look at the principal stress state, it looks something just like the compressive side of it, right? You don't need to rotate too much, right? Basically, you have almost a pure tensile stress, All right. Okay. All right. So what does this tell you? It tells me that I can convert all the stresses in the beam into a principal stress, and I can start investigating the failure of the beam. How so? Because now, if I look at a simply supported beam, I'm drawing the beam out again. All right, and let me just say that I'm gonna do a trick here. I want to take a look at the trajectory of the principal stresses, right? So essentially, I will see that the trajectory of the principal stresses follow this type of line, okay? And being that this is the center line here, and so these are the trajectory of the principal stresses. And knowing that I have tensile stresses like this, right? And tensile stresses like this. Oops, gotta be symmetric. Okay. You say, oh, Bob, I understand. All you're trying to do is draw me my tensile stresses, right? Tensile stress distribution in the beam. Yeah, but you see, where are these lines at, right? As I progress from top to bottom, my stress level increases, right? And now I know that if these are my pattern of tension, we call it pattern of tension or pattern of trajectory, principal stress trajectory. Okay, what we're seeing here is that that's how concrete will respond, and that's how concrete will crack. Okay, so now with this line, the concrete is going to crack in the middle, in perpendicular to these blue lines. So here, remember in perpendicular to the blue line, right? So here, kind of symmetric. So here, okay. Why this turns straight again? Because I have another line here somewhere, right? So I have another line here, right? So here, right? So straight angle. Horrible drawing again, sorry, but try to draw right, straight angle. Okay, so these are my cracks. So these are the cracks. Okay, these are the cracks. Okay, now if I want to extend it a little bit more, I can extend, and I can extend, right? And I can extend this here, and I can extend this here, All right, so what are we talking about? Now, as you know, as I'm getting away from the normal section, my normal stress reduces because my bending moment reduces. So as my section is getting away from the center line, shear stress dominant. So bad that if I draw a straight line here, if I draw a straight line here, if I draw a straight line, this is great straight line. Okay, purple is just a great line, help me. Okay, so I see that it becomes more 45 degree, becomes more 45 degree towards the support. All right, and this crack, okay, we call it shear crack zone, because these are crack predominantly controlled by shear. And same thing here. So this is shear crack. Okay. And if you're smart, you want to note this down because this will happen in second exam, right? Shear crack zone. And in the middle, the crack tend to be more straight because we're in the middle, the flexure stress dominant. So these are flexure crack zone. Flexure crack zone. All right. All right. So what are we talking about? We're talking about that in this case, I will design my reinforcement differently. Okay, so if I were to design for this, my reinforcement pattern will change, okay? Will change. And just a quick snapshot to you that if I design a beam, and this is line up, and I want to provide reinforcement inside the beam. Okay, and I want to put reinforcement here, right? So just say that, and I have two concentrated load, okay? Two concentrated load. Okay, and this is my reaction. So this is PU over 2. Again, this is PU over 2. Same thing. Okay, and I know that my moment diagram looks like this. So moment diagram looks like this, right? So here I have no moment, and then I have a maximum moment right here. Okay, and if this is, let's say a third of L, right? Third of L, right? So this is PU over 2 multiply L over 3, and then in the middle there will be no change of moment, right? The constant moment, right? Constant moment, right? So here again, P over 2, L over 3. Okay, and this is my moment diagram. So this is section moment diagram. And my shear looks quite differently, right? My shear looks like this. At the left end of it will be some shear. In the middle will be no shear, and then at the right hand side, the sign flipped, another shear here. So if that's this positive, negative, so PU over 2. Horrible drawing, apologize. PU over 2. PU over 2 is the same here, horizontal line. This is 0. So side here, negative PU over 2, negative PU over 2. And this is my shear diagram. Shear diagram. Okay, this is my shear diagram. So I have my moment and shear diagram. So I want to design for it, right? So for the moment, I need my flexure reinforcement. That is the bars we talked about, right? Laying at the bottom of the section provide for tension, right? Steel is good for tension. Don't forget, right? So now for bending moment, they're here at the bottom. They're here at the bottom. Okay, all the way through, all the way through. But now note that in the middle section, there's a higher moment and they taper down to 0 as you go into the support. So I may add more to the middle, right? I may add more to the middle. And that's my tensile reinforcement, right? Tensile reinforcement, or we call it flexure reinforcement or flexure reinforcement, right? What you have learned so far, right? Now for the shear, and this is a little bit different now, okay? For the shear, since I only have shear two ends of it, no shear in the middle, I will have only shear reinforcement, like vertical stirrups, vertical like that. Okay, this is side view, okay? Side view like that. Okay, and normally I need to have a hanger bar, right? I need to form a cage, so I need to have a hanger bar so the stirrups have some place to hang, right? Have some place to attach to, right? So this is the hanger bar, right? So this is the top bar. Okay, and these are the stirrups. So let me see, notice that I do not have anything in the middle, right? I also call it web shear reinforcement. slash either some people just call it web reinforcement, okay? Either web reinforcement or shear reinforcement, okay? And if I want to look at the cross section of it, if I want to look at the cross section of it, it should look like just this. So let me pick two sections, right, to ask you to look at. This is AA, okay, and this is BB. What do they look like, right? So AA looks just like this. Means I have bars exposed, so probably like this one here, and this one here, and this one here, this one here, and then top bars here, top bars here. So these are different color to correlate, right? Use different color to correlate. Right here, right here. This is AA, and BB will look like this. And note that AA has no stirrups, right? No shear reinforcement. BB actually has only the tensile reinforcement, one layer at the bottom here, and then I have top bar, hanging bar, and that's the same, cross the beam. And now I have stirrups, which goes like this under the hooks here, and then goes around it and goes up and hooks in here. Okay, so these are how we are providing reinforcement to the section. Okay.
Can you
All right.
screen over to the route? Okay, never mind.
Got it? Okay. All right. So this is the concept of design. This is so-called concept design, right? So I mainly want to show you guys why we have two types of reinforcement. One is flexure, one is shear. And these reinforcements are to be provided based on your moment and shear diagram. Based on your moment and shear diagram. Okay. And now, before I end today's lecture, right? One more thing. So you know how the flexure reinforcement works, right? So think of this, right? So these red cracks, right? You want to basically stitch them. You want to basically stitch them, right? So now you have these tensile reinforcement, which is the flexure reinforcement, right? Go across the crack to stitch them in the flexure zone, right? In the flexure zone, in the flexure crack zone, you have this tensile reinforcement to stitch them across the cracks, right? But in the diagonal or shear crack, or we also call it diagonal crack zone, okay? Diagonal crack. This is 45-degree, right? 45-degree diagonal direction, okay? Keep this number in your head, okay? 45-degree, because I may ask you a question in exam number 2, okay? And this is called diagonal crack zone, right? It's very hard to just use horizontal reinforcement to stitch it over, isn't it? It's very hard. So now to stitch a 45-degree angle, we normally just do a straight line. Okay, normally just do a straight line. And that's why all the stirrups you see are straight line. Okay, just to show you they're the same thing, okay? So these are the shear reinforcement. And that's why they are straight, they're vertical. And you say, Bob, isn't it weird? Would it be better if I do a reinforcement like this, you know, and just stitch them like that and pull the reinforcement through? It would be very hard to do that construction point of view, okay? It would be very hard to do that in terms of construction. So we do vertical, okay? We do vertical. And another added benefit is that when we do vertical, right? And now I want to show you a 3D view, right? So basically these are the stirrups. If I do a isoparametric view, right? Isotopic view, right? So these are stirrups. And again, I'm exaggerating, right? So space out and then another stirrups. Spaced out, okay? Another stirrups. Another stirrups. Okay, so these are my stirrups and I want to put my bars, right? So my bars will go here. See, I have a horrible drawing, right? I have a horrible drawing, but you get the drift. It should be straight, okay? Should be straight. And that's my bottom bar. And I have another bar right on the top of it. And probably not extending that far, right? Probably not extending that far because I only have it here. So this will be here. Okay, I apologize. Everything seems to be twisted on my iPad, but you get the idea. So that's the second layer of bars, right? And know that I have a hanger bar, which is top bar, to connect it, right? To build a cage, right? To build a cage. So that's where the top bar is gonna go through, right? Go through, and again, of course, it might twist it, where everything is twisted. Sorry about that, but that's what it looks like in the isotropic view. It's more like 45-degree 3D view. okay, of the reinforcement cages. Okay. So, ladies and gentlemen, we're done, right? So today, that's what I'm going to end here, right? How we build the reinforcement cages. And next lecture, which is on Wednesday, this week, we will talk about how we're going to analyze the shear resistance given there are shear reinforcement in it. Okay. All right. So I'm going to close out today's lecture, and please stay behind if you have any questions and any concerns, and let's talk about it. All right. Other than that, thank you very much, and see you on Wednesday online. All right. See you on Wednesday online. Okay. Thank you.